All right, class, let's get started with the 1 through 20 electron configuration. I start off with this screen, though, so you can see it. And here's why I did that. You guys know this as the diagonal rule. We also use the periodic table to do exactly the same thing as the diagonal rule. So here's what I want to show you about diagonal rule. I know you've seen this before. It's important, though, that I repeat myself as many times as possible. It doesn't matter what the element is, whatever the element is, the pattern that the electrons fill outside of the nucleus is always the same. And it looks like this. We start here at the 1, and I'm down here at the S. So this is 1s, and I should write that in red. But before I do that, I'm going to use the arrows here to show you what's going on. Okay, so in red, that would be 1s, and that can hold a maximum of 2 electrons. Always 2 electrons for the s, no matter what the number in front is, no matter what the main energy level is. So here I have the 1s2, then the 2s2 comes next. Maximum number of 2 for the s. And then I come back up to the top, and I go to the green, and that would be the 2p. P's can hold a maximum of 6 electrons. That goes back to the guided notes that we've taken previously. And then I go to the red with 3s2. Okay? I'm going to stop when I get to 20 so you can see what's going on. So I got 2, 4, plus 6 is 10, plus 2 is 12. And then I go back up, and when I go back up, I come back up here to the 3p. The p's in green, so that will be 3p6. Now I'm at 18. That means the next part here is going to be my 4s. Oops. In red, which means 4s2, and that's 20. Okay? Now I'm going to flip through this over here. You can see that here is my 1s, 1s2. This one right here would be my 2s2. In other words, 1s1, I should be, hang on a second, I should be more specific when I talk about this. There we go. This right here is 1s1, but over here for helium is 1s2. Okay, so this would be 1s1 if I'm just talking about hydrogen. If I'm just talking about lithium, that would be 2s1, but beryllium is 2s2. Okay, do you see how that works? Here would be 2p. The 2p was in green. So that means this would be 2p1, 2p2, 2p3, 2p4. I hope you're seeing how the pattern works here, 2p5. And then finally, the noble gas here of neon would be 2p6. Okay, so 2p6 if we go all the way across. Okay, and then I go to red would be 3s2 here, that's magnesium. And then I go all the way across to p. Let me get the green again. There we go. And this would be 3p6. I know that's tough to see. Okay, and then by the time we get down here in the red, this is 4s2. Okay, and then I would go into my 3ds, and then my 4p's and my 5s's. Okay, so that's the pattern. So let's go back up here. The element's going to be hydrogen, and then we're going to get helium. So I got 1s1. Okay, there is no short configuration for that. It's just 1s1. The valence is 1 electron. Okay, so that would be 1s1 are the valence electrons. The dot diagram looks like that. Okay, 1 valence electron. Helium, okay, I'm going to go through and answer all of these. So I got 1s2 like this. There is no short configuration. I'll show you what I mean by short configuration. The valence are the 2. I'm not even sure they might not even be considered 2 valence. Helium is a strange, because here, take a look at this. both electrons are on the same side. This is the only time this happens, when there's only 2 electrons. Otherwise, they're going to be separated. So then I have lithium. Lithium is 1s2, just like helium is, and then 2s1. Now here's where, the first time we can have a short electron configuration, or like an abbreviated. This 1s2 is the same as helium. So what I do is I substitute in He in brackets, and then whatever's left over is what I write then for my electron configuration. Notice that these are not shorter, but we are abbreviating it though. So the valence for this would be the 2s1, so that would be 1. Also, I think, actually, let me move these over a little bit, like that, and like that, and like that. So my valence here is usually that 1 electron is gone. So by valence, I also mean charge, not just like what the valence electrons are. Helium doesn't lose any of its electrons. They're basically considered to be core. And here's another one that loses the outside electron as a +1. Lithium would look very much like hydrogen with 1 dot for its dot diagram. So let's keep going here. How about beryllium? Beryllium has 4 electrons. It's got the 1s2 and the 2s2. So my abbreviated would start with helium for the 1s2, and then instead of 2s1, it would be 2s2. And then this one would lose these 2 electrons. These 2 electrons here would be the ones that would go, so that would be 2, a +2. Okay, my beryllium would look like 1 dot, 1 dot. I should write the symbol smaller. Then after beryllium, we go all the way over to boron, which is 1s2, 2s2, and then 2p, and there's only 1 electron there. Okay, again, I'm using helium, like this. 2s2, 2p1 is my abbreviated, and I lose all 3, so that would be a +3. Boron would look like this. 3. Okay, I spaced those dots around the 4 sides, so there's 3 sides with a dot. Now the next is carbon. Carbon is 1s2, 2s2, 2p2, like that. I still have helium as my abbreviated, 2s2, 2p2, like that. Now this, in this case here, carbon can lose 4 electrons, or it can now start to gain 4 electrons, so plus and minus 4. Carbon's dot diagram looks like 1 dot at each side of the box that's around, the make-believe box around carbon. Okay, so let's keep going. Nitrogen is next. Nitrogen is 1s2, 2s2, 2p3, like that. This would be helium, like that, 2s2, 2p3. Now it is more efficient and makes more sense now for the 5 valence electrons that nitrogen have to gain 3 electrons than it is to lose 5. So in that case, the valence for nitrogen would be a -3. And in this case here, if I have 5 valence electrons, for my dot diagram, I go 1, 2, 3, 4, 5. And then we have our first case where the 2 electrons double up. Helium only has 1 side of the box, which is an odd one. That's the one that's different. But that's how we get the 5 valence electrons around nitrogen. And then oxygen, 1s2, 2s2, 2p4. I hope you guys are starting to see the pattern. Oxygen still needs helium as it's abbreviated, 2s2, 2p4. There is a -2 because it has 6 valence electrons and gains 2. Okay, and then I go 1, 2, 3, 4, 5, 6. And there's my dot diagram for oxygen. Okay, now I'm not going to do all of this for you, but I do want to show you what happens once you get past neon, and then see if you can figure out what the pattern looks like after that. It's actually not that difficult to see. So here I got helium again, 2s2, 2, and 2p5. That's going to be a -1 for my valence. And fluorine, of course, has 7. 1, 2, 3, 4, 5, 6, 7, like that. There. Now we get to neon. Neon is the noble gas. This is where everything kind of resets. I got 1s2, 2s2, 2p6. Notice whenever I get to a p6 here, that means I have a noble gas. I can use the previous noble gas to show. So it'd be 2s2, 2p6, like this. There's never a valence electron. Well, not, I don't want to say never, but, and then neon has 8. 1, 2, 3, 4, 5, 6, 7, 8. A full valence shell. Okay, now we get to sodium. Sodium's number 11. Sodium has 11 electrons. The longhand electron configuration looks like we just keep adding. Once we get to 2p6, after that, if you remember, is 3s, and that will be we only need one more. So now I can use neon now. We only use noble gases. So everything after neon. So this part right here is neon's electron configuration, which means everything after neon then we can use just a 3s1. You can see how this really saves us time in writing electron configurations, or at least not writing nearly as much. And because there's one valence electron, sodium only has one, like that, then we have a +1 for its valence. Okay, now this like would be exactly what you would think with magnesium, number 12. It would be, of course, 1s2, 2s2, 2p6, and then 3s2. Okay, that means that we can use neon like this, and then 3s2 as my short form. It's got 2 valence electrons, so they look, you get a +2, and the 2 valence electrons look like that. All right, so I want you to finish this, go through, use the same pattern. Notice that every time we get to a noble gas like neon, the valence goes to 0. I can start over again with the noble gas that we use in the brackets to shorten the electron configuration. So after magnesium, of course, it's going to be aluminum, and then silicon, and then phosphorus, and then sulfur. Let me get down to the bottom here. I want you to finish this up. There we go. Sulfur, and then chlorine, and then argon for my 18, and then it's going to be potassium and calcium at the bottom for the last one. Now if you can finish this up, then you have a pretty good idea as to how to do electron configurations, even the short electron configurations, which we are going to practice. Okay, see what you can do with that.